Hey guys, so sorry I wasn't there today. Happy Wednesday. I'm creating this video to do a full walkthrough of balancing an equation for students that are having a hard time with this concept. I know it can be difficult, or if you missed the day where I went through all the notes and explained how it worked. I wanted to have a full video for you guys where I do a couple examples. So the first problem I'm gonna do is a decomposition reaction of H2O, or water as we know it. That's an ugly O. Let me redo that. So water can decompose into oxygen gas and hydrogen gas. This reaction does not happen spontaneously. It usually would require a electrical current to occur. As you know, water on Earth doesn't spontaneously turn into oxygen and hydrogen, or else it would be a lot harder for us to have that as our drinking resource. Um, okay, so the first thing you'll notice with every balancing problem is there's going to be a space in front of all of the compounds involved. Now, the reason for that is because doing this is to follow something called the law of conservation of mass, which we've learned about. If you don't remember, that law in chemistry and physics is to say that atoms don't just spontaneously appear and disappear in chemical reactions. Anything that goes into a reaction is being released somehow. And this might seem counterintuitive thinking about certain reactions that happen where you have a solid turning into a gas, um, and you're like, okay, well, I started with this solid and now it's gone. But that doesn't mean it's actually gone. A lot of gases on Earth are colorless and we can't see them. So something like a combustion reaction where you're burning a solid into a gas, it looks like your materials disappeared, but in reality, they're just turning into something that we can't see with the naked eye. So remember, to start a balancing problem, the first thing you want to do is take an inventory of what you have on either side of the equation. So first we have hydrogen, and second we have oxygen. So we're gonna take note of how many of each are on both sides of our reaction arrow. And you want to think of the arrow like an equal sign, again, following the law of conservation of mass. We want the number of atoms for each element to be the same on either side of the arrow, so it can help to think of it like an equal sign. So, on the left side, this little subscript 2 belongs to the H. So we have 2 hydrogen atoms. And I'm going to put that right here. On the right side of the equation, we also have 2 hydrogen atoms. So looking at this from the beginning, it actually looks good and like we won't have to do anything. But as you'll see, when I account for the oxygens, that's not exactly true. When we look at oxygen, remember if there's no number with the element, oops, sorry. Not sure why that happened. But looking at the oxygen, there's no number. That means technically there's a 1. But chemists don't write the 1 every time because it would become really redundant and exhausting to write a 1 every time there's only 1 atom in the formula. So you won't see that 1 there, but you just have to believe it's there. And it is. So on the left side, there's 1 oxygen. On the right side, there are 2. So you'll see right now our hydrogen is balanced, but our oxygen is not, which means we need to balance this equation. So, step 2 that we talked about for how to do this is to swap your counts as the coefficients for that element. So with hydrogen right now, we don't necessarily have to do that because we have 2 and 2 on either side. But since the oxygens are uneven, we need to alter them in this way. The coefficient, or the big number out front, is a multiplication factor. So you would imagine that the 2 that I wrote here is being multiplied by both the subscripts in that compound. So the water here, now with a 2 in front, that changes our count on the left side. So now 2 times 2 for hydrogen, we have 4 on the left. And 2 times 1 for oxygen, now we have 2 on the left. So now oxygen looks good, but hydrogen is not matching. The next thing you want to do is think about, with the setup of the equation currently how it is, what could go in this empty space with hydrogen to make it equal. If we have 4 H's on the left and 2 on the right, what can we multiply by 2 on the right to get 4? And it's going to be the same number we had on the left, which is 2. Now, if we check our atom count again, you'll see 2 times 2 on the left, we have 4 hydrogens. 2 times 1 on the left, we have 2 oxygens. On the right side, we have 2 times 2 hydrogens, which makes it 4, and 1 times 2 oxygens, which is 2. Now, again, you can think of your arrow like an equal sign, and you can see that this equation is now balanced because we have 4 hydrogens on the left and 4 on the right, 2 oxygens on the left and 2 on the right. So this example is complete. So this is another example that's a little more involved of a balancing problem. This one is a combustion reaction. Remember, combustion reactions are when a carbon-based compound reacts with oxygen, usually in the form of fire, and breaks into a carbon dioxide species alongside water. And you might be thinking, well, normally when something burns, you don't see water coming off. And in some ways, you're right, you won't see liquid water. But the water that comes off from this highly exothermic reaction is water vapor. So it comes off in the form of steam that will be mixed with the smoke. So again, to start this problem, we want to look at how much of everything we have on both sides of the reaction arrow. For the carbon reactant, there's 6 on the left and 1 on the right. Remember, a carbon on the right doesn't have a number with it, so that means there's only 1. On the left, we have 10 hydrogens, and on the right, we only have 2. On the left, we have 2 oxygens. On the right, there are 3 because there's 2 in the CO2 and 1 in the oxygen, 1 in the water. We add these because they're separated by this plus sign, and 2 plus 1 is 3. So now I'm gonna start this problem by swapping my carbon numbers in their coefficients. So I'm gonna say there's 1 as the coefficient for C6H10 and 6 as the coefficient for carbon dioxide or CO2. Now, if I update my count for carbon, there's 1 carbon on the left. Oh, sorry. 1 times 6, so there's 6 carbons on the left. And 6 times 1, there's 6 carbons on the right. So that looks good. But this 6 here is also being multiplied by our O2. So since the carbon dioxide is 1 compound, we need to also account for the change that happened to our oxygens. So now on the right, there's 6. Sorry, let me change back to my marker. There's 6 times 2 oxygens plus the 1 over here. So 6 times 2 is 12 plus 1 is 13. Now this looks pretty funky, right? Our carbons are balanced, but our hydrogen and oxygens are very much unbalanced. The next thing I want to do is make my hydrogens match because there's a bunch of them on the left and only 2 on the right. So if we have 10 hydrogens on the left side and only 2 on the right and our coefficients are multiplication, I'm going to put a 5 in front of the hydrogen on the right. So now that 5 times 2 will change our right side hydrogen count to also be 10. At this point, our hydrogen and carbon are very well matched, but we need to look at our oxygens again. On the left side, my O2 has not been changed, so there's still only 2. On the right side, remember we have 6 times 2 for carbon dioxide, 5 times 1 for water. So that's 12 plus 5, which is 17. One thing that's important to note is that in a balancing problem, you cannot have any fractions or decimals as coefficients. They have to be whole numbers. So, since on the left our oxygen species is O2, this 17 is not going to work because 17 divided by 2 is 8.5. We cannot put 8.5 on our leftmost oxygen species because decimals are not allowed. So we know that this is only going to work if the coefficient in front of our water is an even number, because the water only has 1 oxygen. The easiest way to turn it to an even number without messing up everything is to just multiply what you have by 2. So my 5 is going to become a 10. My 6 is going to become a 12. And my 1 is going to become a 2. Again, the reason why I multiplied all my coefficients by 2 is because the oxygen we have on the left has this 2, and we can't have decimals in front of them. So it has to be even number on the right and the left. And to do that, this O1 species needs to be multiplied by an even number coefficient. Because an odd number plus an even number is always going to be odd. So now let's redo our counts and make sure everything is up to date. On the left, we have 2 times 6 for carbon, so that's 12. 2 times 10 for hydrogen, that's 20. Oxygen on the left is still 2 because we haven't added a coefficient. On the right side, however, we have 12 times 1 carbons and 10 times 2 hydrogens. If you struggle with your times tables, you can use a calculator during these problems. That is totally okay with me. Now let's look at our oxygens on the right now. We have 12 times 2, which is 24. And then remember this plus sign, we have to add the 10 times 1, which is 10. 24 plus 10 is 34. So now we have an even number on the right, and this is good for us because We can finish this problem by figuring out what 34 divided by 2 is. The answer to that would be 17. And this finalizes our combustion balancing problem by making every element have the same amount of atoms on both sides of the arrow.